Hello guys, let's talk more about acids and bases, and specifically let's start with water. So water is very interesting because it can act as a Bronsted-Lowry base and accept a proton, but it can also donate a proton and act as an acid. This makes water amphiprotic. So let's look at some examples. Let's say that I have a hydrochloric acid, so HCl gas, and I'm going to mix it with H2O liquid. In that case, I am going to form the chloride ion. And I'm also going to form the hydronium ion, the H3O plus aqueous ion. Now here, HCl is our acid forming a conjugate base, Cl minus or chloride ions, and water is going to be the base forming a conjugate acid. All right, so here water acts as a base. Now, what happens when we mix water with a base, for example, ammonia? So NH3, let's call this aqueous, plus H2O liquid, we are going to form OH minus aqueous plus NH4 plus or ammonium ions. So here, NH3 is going to be our base, and hence water is going to be our acid, which actually donates the proton, right? From the base, we are going to form the conjugated acid, and from the acid, we are going to form the conjugated base. So here it's visible that indeed water can act both as a base and accept a proton, and also act as an acid and donate a proton. Now, what's even more interesting about water is that it actually autoionizes. So this means that a few molecules act as bases and a few act as acids. So let's say that I have two water molecules in a reaction and they react with each other. What happens here is that we are going to form H3O plus aqueous plus OH minus aqueous ions. So one of the water molecules is actually going to accept a proton, right? Right here, forming a conjugated acid. So this water molecule right here, the first one is going to be our base, but the other water molecule right here is going to act as an acid and donate a proton and form a conjugated base. Okay, now we can rewrite this expression in a different way using only one water molecule, where we would have H2O liquid giving us H plus ions, which are aqueous, plus OH minus, also aqueous ions. So this is the same expression, only with one water molecule, showing the autoionization of water. Now, what is the equilibrium expression for these reactions? Well, if we look at the first one, we are going to call this KW, W for water. We know that we do not need to take into account pure liquids or solvents in case of the equilibrium constant expression. So we only need to look at the hydronium ion and the hydroxide ion right here. So KW for water, the equilibrium constant, going to equal to the H3O plus concentration multiplied by the OH minus concentration. Now, what's interesting is because this first reaction on top can be also represented with only one water molecule on the bottom, this will also equal to the H plus concentration multiplied by the hydroxide ion or OH minus concentration. So basically, when we are talking about the concentration of H plus ions, it is interchangeable with the concentration of the hydronium ions in aqueous solutions. Now, water autoionizes to a very small extent, only about 2 molecules out of 10 to the 9 molecules autoionize at 25 degrees Celsius. And the equilibrium constant expression, so this expression right here that I just drew, is called the ion product constant for water. And this is indeed a constant value, so Kw equals to 1.0 times 10 to the negative 14th at 25 degrees Celsius. Now, let's talk about the pH scale now. Because the ion product constant for water, so this expression right here, helps us understand the meaning of the pH scale. So the pH is simply a method of reporting the hydrogen ion concentration. So pH equals to the negative log of the H plus ion concentration. And we can take the negative log of this whole expression up here, from where we are going to get that if we add pH to POH, because Kw is a constant, that will always equal to 14. So this is from where the pH scale is coming from. If you add pH to POH, you get 14. So the neutral pH, when you have the same amount of H plus and OH minus ions in a solution, is going to give us a pH 7, which also corresponds to a POH of 7. Now, if we increase the hydrogen ion concentration right here, we are going to have an acidic solution. So this means that the hydrogen ion concentration is higher than the hydroxide ion concentration. However, when we increase the hydroxide ion concentration on this side, we are going to get a basic solution. So the H plus ion concentration is smaller than the OH minus concentration. And remember, when pH equals to 7, we are going to have a neutral solution. All right, I hope this makes sense. Let's talk a little bit about strong acids and strong bases. We know that strong acids and bases actually fully dissociate in water, and there are 7 strong acids, and most strong bases are alkali hydroxides. So we can actually write out the expression for the dissociation of strong acids and strong bases. So let me show you. For example, we have HCl, which is going to dissociate to H plus Cl minus. So it's right here. Now, if this is happening in an aqueous solution, basically the concentration of HCl will equal to the concentration of the H plus ions, because the ratio in the reaction is 1 to 1, so we can calculate the pH from the concentration of the hydrochloric acid in the aqueous solution. Similarly, if you have, for example, let's go with NaOH, it's going to form Na plus OH minus aqueous ions. So here, again, the concentration of sodium hydroxide will give us the concentration of the hydroxide ions in the solution. So if we know the concentration of an acid or a base, and it is a monoprotic acid, and a base that contains only one OH ions, we can calculate the pH of that solution very simply. Let's take a look at that. So let's calculate the pH for a couple of solutions. Here we are only given the hydroxide ion concentration, and in the first example it is 0.02 mole per liters. And we know these nice expressions from the previous slides. So the pH equals to the negative log of the hydroxide ion concentration. But we also know that pH plus pOH equals to 14 due to the ion product constant for water. So if I can calculate pOH, I can use this expression to calculate the pH. And the pOH calculated the same way as the pH, only with the negative log of the hydroxide ion concentration. So in this case, in the first case, our pOH is going to equal to the negative log of the OH minus concentration. So I'm going to take the negative log of 0.020, which is going to give me 1.7. And now I can just rearrange this expression up here to solve for pH. So pH equals 14 minus pOH. So 14.0, right, the 0 there, minus 1.7 is going to give us a 12.3 pH, which is going to mean that I have a basic solution. You can also call it an alkaline solution. Okay, so what happens in the second case? In the second case, we have a significantly smaller hydroxide ion concentration. So what can you conclude based on this? Well, when I have a higher concentration, I have a basic solution. So most likely when I'm going to have a lower concentration, I might end up with an acidic solution, right? That makes sense. I have less OH minus. So let's see. So again, pOH equals negative log of 6.2 times 10 to the negative 9th. And if you do this calculation, you are going to get 8.2. From here, the pH equals 14.0 minus 8.2, which is going to give us 5.8. Indeed, an acidic solution. Although this is not very highly acidic, it is a weak acidic solution. All right, I hope this makes sense. See you in the next video.